Most backends end up looking the same: a database for your main data, a document store off to the side, a search service, a vector database for the AI features, a queue. Every extra service feels like progress the day you add it. 6 months later, it's another bill, another dashboard, another backup plan, another thing that pages you at 2 in the morning. The uncomfortable claim of this video: for a lot of apps, most of that row collapses into one engine you're probably already running: Postgres. Not a rebrand, not a marketing slide. We're opening the hood on every one of these and showing you what actually happens, and where the trade-offs hide when Postgres takes the job. Here's the actual mechanism that makes this possible. Postgres was built to be extended. A real, defined interface for plugging in new data types, new index types, even new query behavior. Some of what you'll see is built into the core. Some is one-line create extension, and the engine gains a new skill. Postgres isn't winning by being a bigger MySQL. It's a platform other tools plug into. MongoDB gave developers flexibility. Elasticsearch gave them search. Pinecone gave them vectors. Redis gave them queues and pub/sub. Postgres asks a more dangerous question. Are those really separate systems, or just columns, indexes, and extensions? Start with the document database. Postgres has a type called JSONB. Store a whole JSON document in a single column. Then query straight inside it. Give me the email of every user on the Pro plan. Drop a GIN index on that column and the query gets fast. We'll come back to why. Schemaless documents sitting in the same database as your strict relational tables. No second server, no sync job, no drift between two sources of truth. Once documents live in Postgres, the obvious next question is whether you can search them properly. Not %wildcard%, real text search. Postgres breaks a document into searchable words, matches your query against them, and ranks results by relevance. It handles stemming, so running matches run. For huge-scale faceting, complex ranking, or typo tolerance, a dedicated engine still wins. Below that bar. Admin tools, docs, product search, you're done. And this isn't some new trend. Postgres started at Berkeley in 1986. Year after year in the big developer surveys, it's both the database most people use and the one most people say they'd choose again. Not hype. 4 decades of engineers not leaving. Now the one everyone clicked for. AI features want a vector database. Store embeddings. Find the nearest ones for semantic search, or RAG. That's pgvector. But here's what every 30-second explainer skips: which index and what you're trading away. IVFFlat builds faster, uses less memory. You pick a cluster count up front. Recall suffers on data it wasn't tuned for. HNSW builds slower, costs more memory. Better recall at query time, no tuning step. It's the default most people reach for now. And the distance operator has to match how your embeddings were trained. Cosine for most modern models, L2 for others. Get it wrong and your nearest neighbors are simply wrong. Silently. One column, not a zero decision column. Location works the same way. The PostGIS extension turns Postgres into a serious geospatial engine. Distances, shapes, regions, the 5 nearest stores to where you're standing. People build entire mapping companies on just this extension. 2 more, fast. Listen and notice give you publish subscribe inside the database. One process notifies a channel, others listening pick it up. And select for update skip lock turns an ordinary table into a real job queue many workers can safely pull from at once, with zero risk of 2 grabbing the same row. Partitioning splits a huge table into manageable date range chunks, so queries only touch the slice they need. Foreign data wrappers let Postgres reach into another database entirely and query its tables as if they were local. Neither replaces a service. They extend how far one database can reach. Add it up. A document store, a search engine, a vector database, a maps engine, and a pub/sub and queue layer. None deployed separately. None monitored separately. One database, one backup, one set of credentials. That's the pitch, and we're not halfway through. The reason Postgres replaces application code isn't only extensions, it's SQL itself. Want a running total? Sum of amount over order by day. No loop in your application, no clever self-join. Every row carries the total up to that point. The same pattern gives you rankings, moving averages, even every customer's third order. Common table expressions let you build a query in clean, readable stages, instead of nesting 5 levels deep. A recursive one walks an entire tree in a single query. An org chart, a category tree, a thread of replies all the way down. Insert on conflict due update inserts the row, or if it exists, updates it. One statement, zero race. Returning hands you back the row you just changed. Together, these delete a surprising amount of application code. Now, suppose your query is slow. You guess it's the API. You blame the front end. You blame the cloud. Then you put explain analyze in front of it. And Postgres tells you the truth. Real numbers. Here's an actual plan. Sequential scan on orders. Cost estimate near 12,000. Actual time 1,200 milliseconds. And look at this line. Rows removed by filter, 48,000. The database read 48,000 rows just to throw them away. Add one index. Run it again. Index scan. Cost drops to single digits. Actual time, 3 milliseconds. Buffers shared hit, 4. 4 pages instead of the entire table. That rows removed by filter line and that buffers line are what you should actually be staring at, not just the headline number. 4 index types worth knowing. btree is the default equality and ranges. Gin is what made the JSON and full-text search fast earlier. Gist handles geometry, the engine underneath PostGIS. Brin is for huge, naturally ordered tables, like an append-only log of events. But an index isn't free performance. It's a second data structure Postgres has to maintain every time your data changes. Add them where reads actually hurt, not everywhere. Picture thousands of people reading and writing the same rows. Who waits? In a lot of databases, everyone. A writer locks a row, readers queue up behind it. Postgres mostly sidesteps that. It keeps old versions around. When you read, you see a consistent snapshot from when your transaction started, while a writer creates a new version alongside it. For ordinary reads and writes, neither blocks the other. This is MVCC, multi-version concurrency control. The honest caveat, this isn't a universal nothing ever blocks guarantee. Explicitly lock a row with select for update, or run at the serializable isolation level, and conflicting transactions absolutely can block or get rolled back. Every update leaves an old version behind, so the database would grow forever. Except Postgres runs a cleanup called vacuum, and auto-vacuum does it for you in the background. When auto-vacuum is healthy, nobody talks about it. When it falls behind, everyone suddenly becomes a database expert in the middle of an outage. Usual cause, a long-running transaction holding old versions open longer than expected. How does Postgres make sure a crash doesn't scramble your data? It writes down what it's about to do before it does it. Every change goes into a write-ahead log, the WAL, safely on disk before the change touches the real data files. If the power dies mid-write, Postgres replays the log on restart and comes back consistent. Log it first, then apply it. That's the D in ACID, durability. That same log does a second job. Stream it to another server and you've got a replica. But a replica is not a magic emergency button. It's a copy. Turning that copy into the new primary is a separate decision, and Postgres won't make it for you. 2 things bite people in production. First, replication is asynchronous by default. The replica is usually milliseconds behind, but under load that lag can grow, and a query against the replica can quietly return stale data. You can make a replica synchronous, but that trades latency for the guarantee on every write. Second, Postgres does not fail over automatically. If the primary dies, a replica does not promote itself. You need something else watching and doing that, Patroni, RepMGR, or your cloud provider's managed layer. Replication gives you a copy of your data. It doesn't, by itself, give you high availability. Reads scale easily. That, well, stream feeds replicas. Spread your reads across them. Writing is the hard part. One primary takes every write, full stop. When that's your ceiling, you partition a big table, or reach for something like Citus that spreads data across machines. You take it on once you've actually hit the wall, not before. One more operational gotcha. Every Postgres connection is its own OS process. A few hundred? Fine. A swarm of serverless functions, each opening its own connection? Memory explodes. The fix is a connection pooler. pgbouncer is the common one. But in pgbouncer's default transaction pooling mode, your connection gets handed to a different client between transactions. That breaks anything tied to a session, prepared statements, advisory locks, and the listen/notes pub/sub we showed you earlier. If you need those, use session pooling mode for that traffic, or route it around the pooler entirely. So does everything go in Postgres now? No. Postgres is not Redis. It is not Snowflake. It is not a globally distributed write machine. A pure high-throughput cache for simple reads, that's still Redis's job. A workload fundamentally about spreading writes across many machines from day one, a purpose-built store will beat bending Postgres into that shape. Heavy analytics over billions of rows, a columnar engine will outrun it. The point isn't that Postgres replaces everything. The point is, it replaces more than most teams assume. Technical power is one reason teams trust Postgres. Governance is the other. It runs on a permissive license close to BSD or MIT, and no single company owns it. It's steered by a community deliberately structured so nobody can quietly change the terms on you. You've watched other open-source databases relicense overnight and send everyone scrambling for an exit. That can't happen here the same way. So the real lesson isn't put everything in Postgres forever. It's simpler. Start boring. Start with the database that already gives you documents, search, vectors, maps, queues, transactions, replication, and decades of trust. And we showed you the real plan output, the real index trade-offs, and the real operational gotchas, not just the highlight reel. Add a specialized tool once you've actually proven you need it. Boring infrastructure isn't a weakness. It's how good systems survive. If that was useful, like, share, and subscribe. Thanks for watching.